Welcome back to the deep dive. If the last few years have taught us anything, it's that, well, relying on a single centralized power grid is a massive vulnerability.
A huge one.
And so we're always searching for energy solutions that offer not just clean power, but, you know, genuine independence and resilience.
And today we're diving into a system that promises exactly that. We've been looking at these excerpts from NovaSpark, Atmospheric Hydrogen Energy Solutions, and it details this modular off-grid power solution. And this isn't just another battery pack. We're talking about achieving weeks of autonomy using one of the most exciting energy vectors out there, hydrogen.
So our mission today is to really unpack the engineering behind that claim. How do you deliver power for days, not just hours, in some remote location?
Yeah, how does it actually work?
We need to understand the unique tech that lets it pull its primary resource, water, right out of the atmosphere, and then convert it, store it, and use that energy in a highly efficient and safe loop.
And this is such a critical deep dive for you, the learner, because the context here is shifting so rapidly. We're moving beyond simple power outages.
Oh, way beyond.
We're talking planned utility shutoffs, increased severity of weather like ice storms or hurricanes, and just the logistical nightmare of fueling remote infrastructure.
And diesel generators are the old answer.
Exactly. They're noisy, they're polluting, and the reliance on constant resupply is a major, major point of failure. This system is designed to just eliminate that single vulnerable supply chain.
Okay, let's unpack this self-sufficient loop because the starting point here is, well, it's almost counterintuitive.
It really is.
When we talk about hydrogen production, you usually imagine these huge industrial facilities drawing massive volumes of purified water. But the NovaSpark system, it seems to completely eliminate that need for an external water source.
That's the hook. That's step 01, water from air. They integrate an atmospheric water module in AWM.
An AWM.
And it captures ambient moisture and purifies it right there on site. You can think of it as a sort of specialized industrial dehumidifier that's designed to work in all kinds of climates.
That one feature, that changes the game for remote deployment, doesn't it?
It's everything.
No pipeline, no trucked-in water supply. If you have air, you have your input resource.
Precisely. And that feature is what enables true self-sufficiency. So if you're operating a communication tower in the desert or, say, a resort in a humid jungle, the only resource you need to periodically put in is electricity, ideally from solar or wind, just to kickstart the process.
That sounds incredible, but let me introduce some friction here. If you're using energy to run a sophisticated dehumidifier to pull water from the air, how much energy does that step one module actually consume?
Right. Does it hurt the efficiency?
Yeah, does it significantly reduce the system's net efficiency?
That's a really necessary question. The source material, it does note that while the AWM requires energy, the overall energy density that you store in the resulting hydrogen far outweighs that initial input cost.
Okay.
Especially when you consider the alternative, the logistics and the high cost of trucking in clean water or diesel fuel.
So for a high resilience application, the trade-off is worth it.
It absolutely favors the self-sufficiency that the AWM guarantees.
That makes a lot of sense. So once the water is captured and purified, we move to the core chemical step.
Yeah, step 2, electrolysis. This is where we take that captured water, H2O, and use that electricity we talked about to split the molecule into its fundamental components.
Hydrogen and oxygen.
Hydrogen, H, and oxygen over O.
And the environmental benefit of this specific type of electrolysis is key here.
Absolutely. Because the inputs are strictly water and electricity, the process generates zero carbon emissions. You're literally just splitting a molecule.
So clean.
The hydrogen is then used as a clean energy carrier, and the oxygen is just released back into the atmosphere.
So the whole five-step flow, which is managed by these intelligent controls, is highly integrated. It starts with OBRO1 water from air, then O2 electrolysis, which leads directly into the storage side, O3 compression storage.
Right.
And after that, you've got O4 fuel cell power, and the whole ecosystem is overseen by O5 controls and telemetry. So let's dive into the hardware specifications that make this storage capability so robust.
When you look at the tech specs of the NovaSpark modular building block, it immediately speaks to scalability. Each module delivers a rated output of 200 kilowatts.
200 kilowatts. Okay, for our listener, what does that translate to in the real world?
It's significant. A single 200 kilowatt module is enough to power, say, a medium-sized data center during a short outage, or run a small community microgrid, or even a major remote resort complex.
And the beauty is the modularity.
The beauty is that you can deploy 2 or 5 or 10 of these units and essentially create a multi-megawatt power plant that's tailored precisely to your needs.
And since we're talking about clean generation, let's just circle back to the output again. We have clean, grid-quality electricity.
Yep.
Water vapor, which is the only exhaust, and optionally some recoverable heat. It's an incredibly neat energy cycle.
It is. It's an elegant loop. And another crucial output metric, especially for applications like resorts or residential microgrids, is the noise profile.
Ah, right, the noise.
Standard diesel generators can be deafening, often running around 85 or even 90 dB. This system is specified at less than 65 dBs at 1 meter.
How quiet is 65 dB? What's a comparison?
Think of it this way. 65 dBd is comparable to the noise level inside a moderately busy restaurant or maybe a running air conditioning unit.
That's quiet.
For infrastructure meant to operate near people, like a hospital or an off-grid resort, quiet operation isn't a luxury, it's an absolute necessity. It avoids noise pollution complaints and lets you be more flexible with placement.
Okay, let's pivot to the feature that truly differentiates hydrogen from batteries, this concept of long-duration autonomy.
Yes.
Batteries are excellent for short bursts, minutes, maybe a few hours, but they really struggle with multi-day resilience.
Exactly. This is the crucial differentiator. The system's storage duration spec is 24 hours minimum, and it extends all the way up to 168 hours.
A full week.
A full week of continuous power. That's what changes the game for critical loads. You're prepared for a prolonged grid failure, not just a momentary hiccup.
And that long duration is all about step 3, storage engineering. Tell us why the specs here matter so much. They mentioned 700 bar pressure in Type 4 composite vessels. That sounds intensely technical.
It is, but the consequences are actually pretty simple. Density and safety.
Okay.
Hydrogen is notoriously light, so to store enough of it to power a 200 kilowatt system for 7 days, you have to compress it significantly. 700 bar, which is roughly 10,000 pounds per square inch, is the current industry standard for getting that high density.
You're packing a massive amount of energy potential into a small volume.
A relatively small volume, yes.
And the Type 4 vessels, why are they key?
Well, older hydrogen storage tanks were heavy steel Type Y or 2. Type Y vessels are these advanced composites, usually carbon fiber wrapped around a polymer liner.
So they're much lighter.
Significantly lighter, and critically, they're structurally safer under extreme pressure. They're designed to manage stress much better than steel, and they're rigorously certified, DOTTC certified in this case, which ensures they meet really strict safety and transportability rules.
So we've made the hydrogen, and we've stored it safely at this high pressure. How does the system then turn that potential energy back into usable electricity? Step 4.
That's the job of the fuel cell. It essentially reverses the electrolysis process. It's a controlled chemical reaction that converts the stored hydrogen and oxygen from the air back into electricity and water vapor.
But I see here it also uses an integrated battery UPS, an uninterruptible power supply.
Yes, and that's crucial.
Why do you need a battery if you have the fuel cell?
Because fuel cells, while they're fast, they aren't instantaneous. They require a few moments to warm up and ramp to full power. The battery UPS provides instant backup during that critical startup window.
So the lights never flicker.
The lights never flicker, the critical load never sees an interruption. It guarantees what they call seamless islanding.
Seamless islanding. Okay, that's a piece of jargon we need to demystify. What does that mean for the operator of, say, a hospital?
It means that if the main grid drops out, the transition to backup power is immediate and completely interruption-free. The system switches from grid power to stored power from that combination of the instant battery and the ramping fuel cell without any human intervention.
So the user doesn't even notice the change.
They don't notice a thing. Seamless means exactly that.
And all of this complex orchestration, pulling water, timing electrolysis, managing compression, balancing the battery and the fuel cell, that's all the domain of the system's brain, right?
Yeah.
The controls and telemetry, step 5.
Absolutely essential. These smart controls handle the entire energy broker role. They decide when to maximize production, maybe when renewable electricity is cheap or abundant, and when to dispense power from storage.
And for remote installations, that must be huge.
It is. The 247 remote monitoring and predictive maintenance capabilities are a game changer. You can run diagnostics and anticipate issues without constantly sending technicians out to these isolated sites.
So let's take these features. The water from air, the quiet operation, the multi-day storage, and transition into real-world solutions. What problems does this system actually fix?
The material highlights several applications where this long-duration resilience provides a massive competitive or logistical advantage.
Let's start with off-grid communities and resorts. The source material suggests the big problem there is the logistical and economic hurdle of diesel.
The cost of diesel is high, sure, but the cost of getting diesel to a remote resort involving boat or truck transport is often exponential. Plus, you have price volatility, the environmental impact.
Right.
A 1 by 200 kilowatt system with 3-day storage autonomy, which they say is a typical configuration, just eliminates those recurring fuel delivery costs entirely. Over time, that saves immense amounts of money and removes a huge supply chain vulnerability.
And what's the timeline?
They estimate power on within 16 to 24 weeks, which is actually pretty rapid for this scale of infrastructure.
Okay, next up, microgrids and resilience for the growing problem of grid instability.
This is where that modularity and the shared storage really shines. When you're dealing with storms or utility-initiated shutoffs, critical infrastructure needs days of power, not hours.
Of course.
So resilience configurations often involve, say, 2 to 5 of those 200 kilowatt systems, all sharing one central large hydrogen storage bank. This ability to share storage across multiple generation units greatly improves efficiency and redundancy.
And these could protect things like municipal buildings or emergency services.
Exactly. Or key utility substations, ensuring they island seamlessly and stay operational for the entire crisis.
And for data centers where any downtime is just catastrophic financially.
Well, traditional backup for data centers is usually dirty diesel generators and batteries that last, 15 to 30 minutes?
Not long at all.
This system transforms the resilience profile. It offers clean backup for hours or even days, and they often deploy them in N+1 redundant fuel cell arrays.
Okay, what does N+1 redundancy mean in this context?
It means that if the data center needs N amount of power to run their critical functions, they deploy N+1 additional fuel cell system.
An extra one.
An extra one. So if one system fails, the extra one immediately picks up the load. It's the highest level of guaranteed uptime, which reflects just how mission critical that data is.
And finally, defense and remote operations areas where logistics are literally life and death.
Absolutely. The ability to generate power from air and renewables means you don't need vulnerable fuel convoys that can be targeted or delayed. The systems are designed to be highly transportable, containerized, which enables rapid deployment in austere environments.
It simplifies the supply chain.
Dramatically. It makes missions safer and far more reliable.
This transition from features to solutions is incredibly helpful, but we can't talk about high-pressure hydrogen without talking about safety.
Of course.
The source material really emphasizes compliance and safety engineering.
Safety is non-negotiable, and they've baked it into the design from the ground up. Hydrogen is manageable, but its properties, it's colorless, odorless, highly flammable. They demand meticulous engineering.
So they follow specific codes.
A lot of them. They adhere to the NFPA2 Hydrogen Technologies Code, which dictates how these facilities must be designed and operated. ASME B31.12 for hydrogen piping, and SAE J2579 for the storage parts.
We're not just listing codes, though. What does following something like NFPA2 mean for the physical installation?
It means the entire system is designed with mandated physical protections. Because hydrogen leaks vertically and disperses very quickly, it's very light, you need constant monitoring.
So detectors.
They install combustible gas detectors at multiple levels throughout the system to ensure immediate leak detection. If a leak is detected, forced ventilation systems activate immediately in a fail-safe manner, purging the area.
And the storage tanks themselves have safeguards.
Yes. Beyond the composite Type 4E construction, the system includes pressure relief devices. If the pressure builds up for any reason, those devices safely vent the hydrogen up through vent stacks.
So it's released high up.
High up, where it can disperse harmlessly into the atmosphere, away from people and equipment.
And I imagine there are emergency shutoff systems.
The last line of defense. The entire system is equipped with multiple, clearly marked, manual and remote emergency shutoff systems that can immediately cut the flow of hydrogen and power in a critical event.
And it's not just the hardware.
No. Safety extends beyond the hardware to the human element. They mandate site-specific safety orientations, operator certification programs, and required annual refresher training. It creates a whole safety ecosystem around the technology.
You started this deep dive looking for a robust pathway to long-duration energy resilience, And what we found in this NovaSpark source material is a truly integrated, self-sufficient modular solution.
It really is.
This system represents a significant step toward energy independence because it can generate clean power from the air and store it safely for up to a full week.
It solves that resilience problem by connecting clean inputs, quiet operation, and the ability to maintain critical services for days, all supported by just rigorous safety engineering.
We've established that this modular system is designed to operate seamlessly across highly varied use cases, from tropical resorts to Arctic monitoring stations. And this raises a final provocative question for you, the listener, to mull over.
The NovaSpark system is explicitly rated to operate across an extreme temperature range, from minus 20 degrees Celsius to plus 50 degrees Celsius.
It's a huge range.
It is. So given this engineered resilience, the ability to generate power autonomously in almost any climate on Earth, consider how localized, containerized power production fundamentally changes the strategic and economic calculus of global infrastructure development.
Especially in regions that have historically been reliant on massive, fragile, and centralized energy imports.
Exactly. What does it mean when you can just drop a self-sufficient power plant anywhere you need it?